Let us now discuss about the impact of second law on engineering, and one example, very good example of the use of second law. That means the use of this the concept of second law is refrigerator. Okay, so actually the refrigerator is run on the basis of a principle known as refrigeration. Okay, so here let us suppose we have, so what is the working principle of a refrigerator? So actually the thing is that we have to let's suppose this is a system and the temperature of the system is Tc. Okay, so in refrigerator what we do, we try to cool down a system, no? So let's suppose the temperature of this system is Tc. Okay, and it is already, let's suppose, cooled. It's already cooled. Okay, this cooled source SOURC. So we have to remove further some heat energy from this system. Okay, and remove the system remove the heat from the system and from here to surrounding. Let's suppose this is your surrounding, or let's suppose this is some other system. Okay, so what we have to do, we have to remove the heat energy from this cooled source to some hot sink. Okay, hot sink. So if you relate this system, or this actually this machine, it will be like this is your refrigerator and this is your surrounding. Okay, so actually the room temperature of the surrounding is what, almost let's suppose in normal condition it will be 25 degrees Celsius now, and the the inside the refrigerator the temperature we want below, below 4 degrees Celsius. Okay, so actually to make the system, that means inside the refrigerator, we have to remove heat energy from the refrigerator, no? To the system, to the surrounding. So actually this process, we cannot, actually this process is not a spontaneous process. Okay, so let's suppose the temperature of the hot source is Th. Okay, Th, and this is hot sink. Okay, so suppose we have to remove Tc amount of heat from the cool source to the surrounding, that means your hot sink. Okay, to cool down this source further up to 4 degrees Celsius, let's suppose. Okay, but this process is not spontaneous. Why, you see? So if you try to calculate the entropy change, we know that entropy change is what, dq by dq reversible by your temperature at the temperature at which the machine is running, no? So but here actually in this case the change of entropy is actually the combination of these two, no? So it will be like here in this part, if you consider this section. Okay, this section of this machine, then what will going to happen here the heat will going to remove from this source, no, cold source, then it will be what, remove. So remove means heat will going to be removed, that means we have to use what, minus symbol. Okay, okay, and the heat will going to remove, understand, and heat will going to remove, that means the entropy change for this part will be what, minus qc by t, understand. And again that amount of heat will going to be, we will going to remove from this part, and we will going to we're going to actually put this amount of heat into what, into this sink now. So that means the entropy of the system will going to what, it will be plus, because we have to what, we have to remove from here. Actually this is for negative sign is due to the removal of the qc amount of heat. Okay, and the same amount of heat we want to insert in the hot sink. Okay, or then what we have to do, we have to use a plus symbol, because we are going to insert, okay, we are going to add that amount of heat into that sink. Okay, hot sink, so it will be plus qc, same amount of heat, na? So we can use qc, and but here it will be what, tc, na? Tc amount of heat. Actually the temperature of that this part is what, tc, but here we add in this part, in this hot sink, we add QC amount of heat, okay, which is actually removed from here, understand, and this amount of heat we will going to add to that hot sink. So but the temperature of hot sink is what? TH, so we have to add here TH, okay. But here if you simplify this one, that it will be what? It will be your TC, actually same thing, okay, QC plus QC TH, okay. But the interestingly the thing is that we know that the hot sink is, that means the temperature of the hot sink is higher than the temperature of cold source, because this is your surrounding, no? Let's suppose at normal condition it is your 25 degrees Celsius, and the normal but the temperature of the cold source is lower than 25 degrees Celsius now. So that means TH is higher than TC, okay. So if TH is higher than TC, let's suppose this one is higher than this one, then the del S value will be what? It will be less than 0 or greater than 0. See, if TC is less than TH, okay, that means this negative, because this TC QC and QC are same, okay, so that means the overall this part will going to be, this negative part will going to be, this is positive part, no? This will go to, let's suppose this is positive part, okay, this part is negative part, so this negative part will be higher than the this positive part, no? Because TH is higher than TC, understand. Since TH is higher than TC, you can use like this, okay. So let's suppose amount of heat, amount of heat is, let's suppose 2 kilojoule, let's suppose 2 kilojoule, okay. So if it is 2 kilojoule, then it is also 2 kilojoule, okay. Suppose TC is equal to your let's suppose 10 degrees Celsius, okay, then it, and here it will be your 25 degrees Celsius, okay. So this part will be what? Less than this part now, because this is divided by 25 but this is divided by 10, so the overall change of entropy will be what? Negative, understand, no? So the overall entropy will be negative. So we know that from the second law of thermodynamics, that if del S is equal to negative, then this process is not a spontaneous process, okay. So remember this point, okay. For we noted the for from the second law of thermodynamics, we know that uh, for a spontaneous process, the entropy is always increasing. Entropy is increasing means what? The change of entropy is increasing means what? The change of increasing change of entropy must be always positive. That means increasing, no? It must be always positive for spontaneous process, okay. So if we are saying that the process is spontaneous, that means the entropy is increasing, that means entropy is positive. But in this case, you see, we have found that del S is equal to negative. That means the refrigeration process, okay, refrigeration process is actually a non-spontaneous process. That means del S is equal to what? This is, in case of this one, is del S is equal to negative. So the physical meaning of this is that this is your cold source, okay. So that means this is your cold source. Let's suppose the entropy is this amount, okay. So and the entropy changes here, the entropy change is very small. What is the meaning of this one? Negative means the change of entropy, the final change of entropy is lower than the initial change of entropy, understand. That then only it will be negative, no? Okay. So to actually to make it positive, what we have to do? We have to actually add some, so we have to do some external work on that system, okay, to make the process spontaneous, okay. So let us now discuss about how we're going to do some work, okay, or how amount, or what amount of work we have to do to make this make the process spontaneous, okay. Suppose this is the new setup. uh, Here we introduce a new machine, or a machine here, by using which actually we can remove QC amount of heat from that cold source to that hot sink, okay. and we have to do some work, okay, but to remove that QC amount of heat, because this process is not spontaneous. Now previously we already understood that if we don't use any machine, then we cannot actually remove QC amount of heat, because entropy is what, less than 0, okay, in such cases. So we have to, here we, what we have to do, we have to make entropy is greater than 0, okay. So this is the main objective. So here you see we have to apply W amount of work, or we have to do W, we have to do, we must have to done W amount of work on that machine to remove QC amount of heat from that cool source, okay. So when we remove QC amount of heat from that cool source, okay, then here you see QC amount of heat is removed, okay, from that cold source, and we add additionally W amount of work, okay. So the total amount of energy is what, W plus QC. So W plus QC amount of total amount of energy is this one, na? This one plus this one. So that means in the hot sink, actually QC amount of heat is not added, okay. Here we are not going to remove, actually we are not going to introduce QC amount of heat to the hot sinks. We are actually going to introduce QC amount of heat plus W amount of energy to the hot sink. Understand this point? This is a very important point, okay. So let's suppose the amount of heat which is actually added, or we are going to introduce to the hot sink, is, let's suppose, QH, okay. So here QH amount of heat we will going to introduce, okay. So since we will going to introduce this one, and actually by removing what, this amount of heat, na, this amount of heat and this amount of work, that means QH is equal to actually what, W, okay, plus QC. Understand? Actually the QH amount of heat actually is equal to the W, which we have done some work now. We have done some work to that machine to remove the QC. So total energy is what, QC amount of heat is removed from the source plus W. So this is the total energy, okay, which we actually introduced. And let's suppose that energy is QH. So QH is equal to W plus QC. Again, the thing is that since here we just, here we remove and we remove, okay, here we actually we done some work, okay, and here also by doing some work we remove this amount of heat. So these two are positive, okay, these two are positive, but here we introduce na, so this will be your negative. This is coming conventionally, okay. So actually so remember this point, okay. Why the negative is coming? Negative sign is coming because what, we are going to introduce QH amount of energy to that sink by removing this amount of heat from source and this amount of work from that machine. So this amount of work is removing, okay, and this amount of heat is removing from the machine, okay. So finally we are going to removing this plus this amount of energy, okay, and that removed energy is actually introduced to the hot sink. So we are going to add minus plus plus, or even we can use, since we are removing this amount of work and this amount of heat now, so we can write here minus or here minus, okay. If you try, if you don't understand, then you can also write this way. We are going to remove the W amount of work and QC amount of heat from that machine na, so we are going to remove, and we are going to introduce na, here where we are going to introduce QH amount of heat, so we can even write here plus, same thing. So what we can write here, minus QH is equal to W plus QC, okay. So this is the heat actually which is actually going to introduce to the sink, total amount of heat, okay. Understand? So now the thing is that how we're going to calculate how much work we have to do, or we have to do to remove QC amount of heat from the cool sink. So we can calculate this one by using some terms. Okay, a new terms, actually one new term is introduced, and by the scientist, actually that term is known as coefficient of performance. Okay, performance. So coefficient of performance, so it is actually symbolized as small c. So what is coefficient of performance? Actually coefficient, how actually if we have to add, less amount of work to remove qc amount of heat from that source. Okay, less amount of work to remove qc amount of heat, so we that means the performance is good. Okay, if we have to add more amount of work, or you have to do more amount of work to remove the same amount of heat, then the performance is not good. That means the performance of the machine is not good, na? So here actually the c represent the actually the performance of the machine. Okay, so here we can define the c by using this okay, it will be like this one: energy which is transferred transferred as heat. Okay, as heat, and energy transferred transferred as work. Okay, so actually this is the definition. Okay, so what is the definition of coefficient of performance? So the definition is that if we have to do less amount of work to remove a specific amount of heat from the uh, cold source to the hot sink, then the coefficient of performance is good. Okay, understand? So this is the definition. So what we can write here, so here it is what energy transferred as heat. So how much energy is transferred as heat? Actually heat, qc amount of heat is actually we remove qc amount of heat from that cold source, no? So it will be what, your qc amount of heat we are going to remove. And how much actually work we have to do? So let's suppose we have to do w amount of work to remove qc amount of heat from that cold source. Okay, so it is your performance. Okay, so we can even write this one by c is equal to w by q c. Okay, so here you see we have already the value of w. So you see from here this equation, so this equation we can write w is equal to what? W is equal to minus qh and minus qc. Okay, so we can put this value here. Okay, so it will be like minus qh, okay, minus qh minus tc divided by, sorry, this is qc. Okay, minus qc divided by qc. Okay, so it will be like what? It will be minus qh divided by qc minus 1. Understand? So this is your 1 by c. So up to this I think you understand. So we have this formula. Okay, so now interestingly we will going to use a very important relation. Okay, so actually we have already proved one relation in the previous video. Okay, if you go through that video, the video was ds is equal to 0, first step. Okay, first we actually proved that the entropy is a state function for a particular type of cycle, no? So go through that video. Okay, so you are going to get a relation like qc by tc is equal to minus qh by th. Okay, we have already proved this one. It is actually in the justification part. Okay, so you can even go through the your Atkins book. The page number is actually, okay, wait, I'm going to tell you the page number 83. Okay, 83, page number 83 you can go. Okay, so if you go through that page number, then you can also get this relation. Okay, page number 83. Okay, so here so we have this value qc by tc is equal to minus qh by th. Okay, So here what we can so here you have what you have that QH by QC. Okay, so we can cross multiply this one, so we need actually minus QH by QC is equal to what? QH by QC is equal to your TH by TC. Okay, QH by TC. Okay, so what you can do, so you can put this value actually, so you can put this value in this relation. Okay, so I'm again going to write this relation. Okay, so the relation is actually 1 by C is equal to minus QH by QC minus 1. Okay, so here we have this value. Okay, we can put the value of QH by QC uh, here. Okay, in place of QH by QC we can put this value TH by TC. Okay, so if you put this value TH by TC minus 1. Okay, understand? Clear? So here it will be what? TC TH minus TC 1 by C 1 by C. Okay, understand? So it will be what? It will become C is equal to TC by TH minus TC. So this is your final equation. Okay, so if you know the temperature of the coal source and the temperature of the hot sink. Okay, so that means if you know, if you I think you can we can easily measure no temperature by using a thermometer. Okay, we can measure the temperature of the coal source, which is your TC, and we can even measure the temperature of the hot source, which is TH. Okay, by using thermometer, and we have that data now, so we can put that value here and we can calculate the actually coefficient of performance for a refrigerator. Okay, understand? The physical significance or physical meaning of this whole process is that here, let's suppose this is the change of entropy. Okay, so here we introduce some work to increase the temperature of the hot sink. Okay, to actually increase the entropy. Okay, so in previous case we have already observed that in entropy, since in this hot sink is lower than the change of entropy in this in case of cold sink. That means the here, let's suppose this is S1 and this is S2. Okay, previously if you don't use that that machine, so it will be like this one, no? If you don't use machine, then it will be your just simple this one, QC. So it is not possible because why? The amount of this entropy is actually higher than the amount of this one. So if this one is S1 and this one is this one is S2 and this one is S1, then actually S2 minus S1 is equal negative. Okay, because this is less. So if del S is equal to negative, if del S is equal to negative, then it is your what? It is just not a, it is not a spontaneous process. Okay, so in this case, what we do, we just apply some work to increase the temperature, or to if we can increase the temperature or increase the heat energy of the system, okay, of this sink, then what will going to happen? Then the entropy change will going to increase. That means randomness will going to increase now. That is the physical significance. Okay, so by actually introducing this work, we are just trying to increase the entropy of the system. So here it will be, let's suppose S2, this is S1. So that means by introducing this extra heat, the work energy, we are just trying to increase this, okay, this amount of the amount of entropy of the hot sink by some amount, such that, or such a way that this will going to cancel out this one. That means this will become equal or more than this one. Okay, then if the entropy of this one is higher than this one, that means S2 minus S1 is equal to higher than 0. Understand? So that means the process will going to be spontaneous. So this is the physical significance or physical meaning of the the work, why we actually use work, or why we actually uh, do some work on that machine. Okay, actually we do the work to increase the what entropy of the hot sink, or to increase the randomness of the hot sink, okay, such that the process will going to spontaneous. Thus we have this relation, okay, by using which we can calculate the actually the coefficient of the performance, okay, excuse me, coefficient of performance of that refrigerator. Okay, so but the thing is that in practical machine, so here let's suppose this is your refrigerator. Okay, so this is the inside of the refrigerator, let's suppose this is the inside box. Okay, so but the thing is that there will be some leakage always there. We observe some leakage. Okay, let's suppose the leakage is a minus th minus tc, let's suppose. Okay, excuse me. So if the leakage will be this amount, then there will be some loss of energy. Okay, so what we have to do, we have to maintain the, so let's suppose this is the temperature of that tc, that tc is the temperature of the cold source. Okay, so this is the inside of the refrigerator. Okay, the temperature inside of the refrigerator. So actually since we cannot make the wall impermeable of the heat. Okay, it is not possible. Okay, so a little amount of heat will always going to be lost from that inside of that refrigerator. So it is not possible to make a totally insoluble sorry what impermeable walls. Okay, or even when we open the door, then also some temperature will going to be changed. Okay, that means the temperature of the inside of the refrigerator will going to change if we open the door also. Okay, so let's suppose the leakage is you know defined by a constant a into th minus tc. Okay, so actually we have to actually, so we have to uh, apply actually a minimum power, let's suppose p, to maintain the original temperature, that means which is tc of inside that refrigerator, by pumping out the energy by heating the surrounding. Okay, so again we have to do some work now, compress the things that this is your machine. So again we have to do some work uh, to increase the entropy of the hot sink, to remove some amount of heat from that cold source, to maintain that temperature tc. Okay, so let's suppose this power is the minimum power is p, and actually this is given by 1 by c into a th minus tc. So this is the formula actually. Okay, and here actually if you put the value of c, then it will be like a into tc by th minus tc square. Okay, so that means we have always we have always apply this amount of minimum power to maintain the temperature inside the the refrigerator. That means to maintain the temperature constant, that is the temperature of the refrigerator inside the it's actually inside the refrigerator. We have to uh, apply some minimum amount of minimum amount of power. Okay, so let's remember this point. So that's why it is a very that's why in the hot days we have to mainly the air conditioner or the refrigerator actually. Okay, it will going to consume more powers. Okay, understand, because there will be more leakage will be there than in mild days. So that's why to actually to make the temperature of the inside of the refrigerator, we have to apply a minimum amount of power. Okay, understand? Hope you understand this, the principle or the theory behind the refrigerator or refrigeration process. So next class we're going to discuss about the thermodynamic temperature and Clausius inequality. Okay, so thermodynamic temperature is also not a difficult topic, but the Clausius inequality is a interesting topic. Okay, so basically we know that ds is equal to what, is equal to dq by t, no? This is for reversible process. Okay, but you know, this is for reversible process, but what about the or irreversible process? Okay, actually there will be some inequality will be there. It will be like ds is greater or equal to the dq by t for other process. Okay, so we're going to discuss about this. And this inequality, this is not equal, inequality, and this inequality is explained by Clausius, and that's why it is known as Clausius inequality, or that this equation is actually known as Clausius inequality. Okay, so we're going to discuss this in detail in next class. Okay.